Okay. I was going to make a joke about AGI and presentation systems, but it worked the first time. All right, so good morning, everyone. Very, very nice to be here. Just to clarify one of the points that Andrew made, I'm not here to do a favor to a friend, although I absolutely enjoy sort of conversing with him as well. It is about absolutely meeting smart people. That's one of the things that, keeps me from aging mentally. So this talk is about, systems engineering, systems thinking, and it explores whether the systems engineering pieces are going to be on the rise. It's a bit of an opinionated take, so yours could be different, and we should debate it out in the Q&A part of the talk. That's where the question mark is. It's more of an exploration. The outline of this, I wanted to lay it out because I can ramble on sometimes. We'll start with defining systems engineering in the context of this topic. And with the lens of that definition, we will explore whether accessibility of programming has been the same as accessibility of systems thinking in the last 20 years. And at the end of it, I'll share why I am bullish on the rise in systems engineering for the next decade at least. So yeah, in the glorious tradition of the sciences, we'll start with definition. Who can help me define? How should we define systems engineering? Any thoughts? Like one of the things that is often talked about is systems languages versus, I don't know, JavaScript.
Getting to the bottom of things.
Getting to the bottom of things. And I think Andrew had a fantastic talk on that in the first Systems Distributed Conference in Cape Town. I'll strongly recommend you guys take a look at that talk as well. So that's one definition that we have. Measure. Okay, so can I say that as keeping things like quantitative at least, keeping it a little more concrete than amorphous. Okay, what else?
Methodology.
Methodology. That's very interesting. All right.
Real world trade-offs.
Real world trade-offs. Yeah, I mean, so the sort of making decisions and being conscious about what you gain versus what you lose. Okay, fantastic. Anybody else before we move on?
Systems and multiple parts interact.
How parts interact. Okay? Management of resources. Good. A lot of different things are coming out, and the good part is that each one of those, there was not a single one which I would disagree with. But for the purpose of this talk, it's closest to what you defined, which is different parts and how they interact, right? So for the purpose of this talk, I'm going to define this as designing and using abstractions that help make a problem computationally tractable. Okay, bunch of loaded words, two in particular. One is abstractions, second is computationally tractable. The abstractions piece captures the relationship part of it because you've got a bunch of moving parts. If we cannot have a bunch of interacting parts, it's very difficult to think about it as a system. So how they interact, what are the abstractions with which we define those interactions, that captures the abstraction part of it. The computational tractability becomes very important because these relationships, these interactions can be done intelligently or they can be done in a way that just leaks all over the place and makes a mess of things. Which is why, these, I'm being very particular about both of these points in defining systems engineering. The computational tractability part is specifically a bit loaded, so I'll encourage you to not get stuck up on the term. All that I mean by that is subject to reasoning and analysis. It's there's actually a very good essay by Jeanette M. Wing called Computational Thinking. Anybody here who's gone through that? Okay, so Yoran has. I think it was 2006, CSEM, Communications of the ACM, where she wrote this essay. Fantastic piece of work. She was, I think, the co-author with Barbara Liskov on the Liskov substitution paper, 94, 96, when that paper came out. And if I remember correctly, she was the co-author on that paper. Fantastic way of articulating a lot of thoughts. So instead of repeating her points, I'll encourage you to read that paper. So let's get to tractability. Who can, like, anybody wants to share what this is?
Yes. Brain fuck. This is brain fuck. It's a that exists.
Yes, this is BF. So let me maintain the sanctity of this podium. So I agree, and I've been very liberal with my choice of words in front of students, but this is there's a code of conduct here. So BF is a fantastic language, and can anybody tell me what this is? Like, what is written here? Hello world. Okay, because that's the thing that shows up on Wikipedia, right? Guess what? It's not. Because I was expecting a hello world answer, because the only way you can actually parse this is by guessing or by executing. Like, this is not computationally tractable. We cannot look at it and figure out in a bounded way, like it is bounded purely in our mind. We cannot actually, I cannot do a good job of figuring out the answer. Even hello world. If I remember correctly, this is something like nothing to see or move along types statement, but I can't be sure, because its level of abstraction does not yield to computational tractability on this point, which is figuring out what it means. It has only 8 operators, right? Increment, decrement, increment data pointer, decrement data pointer, in, out, and I think jump and loop if not 0. So those are the 8 instructions. It's closer to like a VM in that sense. It's closer to an ISA. Right, so tractability is important. Just because something is Turing complete does not make it tractable. That's the point that I was trying to make here. Another point is that small does not necessarily mean beautiful. Right, we've got to be clear that we are able to reason what is going on, and that is what makes it a good abstraction. And in fact, I think yesterday there's a whole bunch of good properties enumerated by Sujay and James, if I remember correctly. And all of those properties hold, I think. Let's take a look at another example, because it's very easy to get into systems definitions at a very, very machine level. I wanted to give more of a product lens to computational thinking. This is a warehouse. What you're seeing up here is a bunch of storage spaces. I come from an e-commerce background, and so I thought I'll just throw in a bit of e-commerce as well. There's a receiving zone, forwarding zone, goods are kept, people go collect goods, bring it up, to a staging area, and it's sort of prepared for shipments. What does this remind you of? What do you see? Are there any analogies that come to mind? CPU. Yes. What about CPU?
Like levels of cache and then separate goals.
Precisely, right? So there's a cost there's a distance cost to the goods, right? And actually getting those goods. So you've got like this caching area, which is the staging zone. In fact, the data warehouse people here would know the history of a lot of their terminologies actually come from literally the warehousing space, right? So yeah, let's say we've got an engineer who was asked to design a warehousing system, and they ended up modeling, like every product is being tracked, when it comes in, when it goes out, all of those things are essentially happening through a computer system. But guess what? They've not modeled the distance. They have the notion of where a product is stored, but there's no notion of distance in their system. Do you believe such a warehousing system to be computationally tractable? There's no tractability there. You have digitization, but you don't have tractability. And this is actually a very, very common theme where you would, you would just start doing exactly what you had been doing earlier. You would just start doing it online without applying computational thinking. And this is why computational tractability was so important. Another good example was by a friend of mine. He was sharing an insurance. So he used to work for one of the world's largest insurance brokers. And what they had was a bunch of emails being exchanged whenever there was a good lead for a customer that would actually come in. And they would make a bunch of decisions and something would go out. And they brought in like a $5 million worth consulting contract to digitize or digitalize. Sometimes that's the word that also gets thrown around. And all of that email system essentially moved to web forms. The process remained exactly the same. Okay, so you've got just your input and output mechanisms that got changed, but there was no computational thinking that was actually brought in. And that deprives us of so much goodness, when we think about it like that. And that's a big reason why I'm talking about all of this is because I feel systems thinking, needs to get elevated far more to higher level products and not just be limited to the closer to the metal side of things that we are normally used to. In fact, even organizational designs, actually, there's so much systems thinking that we can bring in. This was so crucial that in my current company, I actually created the notion of a product engineer, specifically to focus around bringing systems thinking to how we think about a product. I actually did away with the idea of product manager because they tend to insulate engineers from the domain. And if the engineers do not comprehend the domain, they cannot model it in a computationally tractable way. Okay, so this is something that all of us should be pretty, should be fairly clear that abstractions are layered and contextual, right? For example, let's say that the bottommost layer is the operating system, how my process is interacting with the operating system. The next one could actually be, how the memory movement is happening within the process. In the next layer is some of the domain pieces. And at a higher layer could actually be how it is interacting with some of the other services. So these are layered, and each one of these layers has a certain nouns and verbs to it that helps us model things better. The reason why I'm talking about this is that because of this layering, we often need to move between these layers as we are thinking about a problem. So I built an app. When I start thinking about how to make it performant, I often need to go a few layers below. When often enough, when we are thinking about logical layers of a product, we need to elevate our thinking and get into the higher planes. This continuous traversal is something that the best engineers that I've worked with do in an extremely efficient fashion. And this is what Janet Wing meant when she talked about computational thinking means more than being able to program a computer. It requires thinking at multiple levels of abstraction. And this will become more relevant when we talk about the last 20 years and how a lot of the belly of engineering has evolved. Let's take another look. Printing money. There was an issue that happened with an Indian bank, but the nature of issue is not unique to India. It's something that could actually happen in pretty much any geography. So India has this notion of these interbank transfers mediated by an organization called NPCI. So the block on the left is one bank, the block on the right is another bank, and you've got that intermediation being done by NPCI. The Finacle app server that you see is actually the core banking server. IMPS is one of the sort of settlement protocols that banks use to speak to each other. So what happened was there was a particular exploitation that was done by a few, we are yet to conclusively know whether it was malicious or whether that was accidental. But what was happening was, if you transfer money from that bank to this, the money would get rebounded to the customer who sent and would get credited to the customer who received.
Nice.
Okay? So this is known as printing money. The QR code is the link to the actual article written by Anand V, who's a security researcher. He's actually, more than a security researcher, but fantastic article and something that I'll encourage all of you guys to actually do. Why do you, any guesses as to how this became possible? Non-atomic, okay? That it has to be non-atomic, otherwise, that's clearly one thing. So clearly transactional boundaries are being breached, right? Because normally you will have debit and credit sort of being baked into the same transaction. So if you roll it back, then you get to a more consistent state. But so one of the things, sorry? Violation of trust boundary. Fair, yeah, that actually was one of the things that was happening. Yeah? Yeah? Sorry? Multiple sources of truth. Was that the same thing that?
I was saying JavaScript.
Yeah. So multiple sources of truth in case of a CBA, in case of a core banking system, usually doesn't happen. But I can see why one would think about it. The problem was that the idea of a transaction was crossing trust boundaries, which is what you ended up talking about. And when I don't have sufficient time to get into the details of it. I'll encourage you to go through it. The point that I was trying to make is that this became possible because the primitives that the systems were operating in allowed it to happen. The debit and the credit. The moment the money came in, there was credit that happened from inwards into this bank, and it sort of bubbled up the credit upstream and sent a reverse debit message back. This becomes possible when at the application layer, you allow manipulation of these primitives. If manipulation of these primitives was not operating at the application layer at all, it's not possible to actually have these issues. Right? It's not too different from how programming languages often enough prevent you from doing a few things. It's quite akin to that. Okay? So the reason why I brought this up is that bad abstractions tend to leak in ways that shows up as very complicated issues at times, and the cost of that is not usually talked about in the industry. There's a huge cost to bad abstractions. When I came across this article, I immediately sent a mail to Yoran a message to Yoran that you got to talk a lot about these sort of issues. That if the fundamental primitives with which people are operating, if for example, if double entry is something that is being completely closed in a guaranteed abstraction boundary, that prevents mistakes from happening. Okay? So yeah, this was an example of leaky abstraction. And if you go through the article, one of the things that would stand out to you is that I tried putting myself in the position of the architects who designed those systems, and I realized that one of the issues that we often encounter as architects is distance to reasoning. We are working with some primitives. If those primitives do not allow a bounded reasoning, with the code in front of us, it's super easy to make mistakes. It's super easy to get into these sort of failure points. Okay. Yeah, async await is actually another such example, because what it does is continuations tend to create a much bigger distance across which we are reasoning. But when the same thing we end up writing is in async await fashion, that distance ends up reducing considerably, and that allows the fixed stack in our mind to operate in a tractable way. Okay, so yeah, that was about abstractions having cascading effects. Let's look at the last 20 years after having talked about some of these abstractions and their definitions. Who here considers JS to be a good language? JavaScript. Okay. only 3 hands? Okay. How many consider JavaScript to be a bad language? Okay, a lot more hands and a lot more, okay. How many consider, independent of this question, how many consider JavaScript to be good for the industry?
For the industry?
For the industry. I'm treating that as a separate question from the design of the language, okay? Define good. Yeah, but then, I get it. Systems conference definitions are important. Fair enough. So I wouldn't express my opinion right away. Let's get to this. Okay. I want to review 4 fundamental sort of milestones that happened. The first one was the launch of iPhone in 2007, followed quickly by the launch of Android in 2008. App Store again launched in 2008. What it did was it suddenly brought internet 24/7 in front of the consumers. Before that, that was not the case. When we were out there, strolling, taking a walk in the park, sitting on our toilet seats, we were not glued onto the internet. And that behavioral change was important. Okay. The second thing that I want to talk about is JavaScript. And some of you might be wondering, why am I talking about JavaScript just around 2010? Because of the launch of Node. JavaScript had been a general purpose programming language much before that. But its pervasiveness in the stack of a usual service or a usual application or website really took off after the launch of Node. Okay, and specifically, when NPM launched in 2011, things absolutely exploded. And as I say, the rest is history, buried under 256 GB of Node modules. Another major change that happened was the launch of GitHub in 2008. Git was launched pretty sort of close to that. What GitHub did was it introduced new abstractions in the form of PRs, okay, which was an abstraction that was distinct from the workflows that actually existed in Git. Not a lot of workflows actually existed in Git, but so GitHub introduced very good abstraction, and open source existed before that. But at least as a programmer, I can clearly see pre-GitHub open source very distinct from the post-GitHub open source. And again, things like Node.js, the NPM packaging and stuff like that, contributed all of that to the explosion. Lastly, AWS launched in 2006. But again, as a user, I find that as they started working on PaaS, things exploded a lot faster. There's also a ZERF phenomena, which people talk about. The zero interest rate policy, which was a time frame from 2008, the post-financial crisis situation, up till about 2015 or something, and then for a couple of years in 2020 to 2022. People talk about that as the explanation behind a lot of over-capitalized technology industry. I don't quite agree with that. It has its role to play, but I feel that it's distinct. I feel these 4 factors that I spoke about, smartphone launch, JavaScript, Node.js, that ecosystem, GitHub, and cloud. These 4 things really happening in a really close span of time exploded the accessibility of programming. Okay? And what happened was this is what smartphones did, and what that created was a need for an app for that for every kind of thing, which then entrepreneurs like me sort of latched onto that and said, we need more developers, and JavaScript came to the rescue, and that was not sufficient clearly, because there's so many low-hanging fruits. Because consumer behavior, because of the smartphones, changed so dramatic. I cannot emphasize on this enough. Whenever consumer behavior changes, there are radical seismic shifts that the industry goes through in terms of the abstractions and the economic opportunities. This was still not sufficient. So more developers, the opportunities seemed endless. And then obviously, if there are, endless opportunities, there is supply of capital that's available. So obviously the JavaScript ecosystem also stepped up to that. And I mean that in a good way. Okay, I mean that in a seriously good way. The language definitions became a lot better. The abstractions quality actually became a lot better. The runtime ecosystems became a lot better. So all of that actually happened for the good. But one thing that didn't, one thing that was not good was that because of all of this need and this huge ability to make a lot of money, it became easy to just get trained in some of these technologies without necessarily having the foundational thinking of systems engineering. And it was sufficient. Just being trained on how to write an app was actually sufficient to make enough money. So a lot of engineering converted into factory, what I refer to as factory development. Factories don't deal with why, they focus on how. Okay? And so what all of this did was Lego-like assembly leading to computational thinking not being a necessary criteria. Okay? We also had the development of the rise of the full stack engineer. They knew backend, whatever that means. They could administer Kubernetes, know some kernel level stuff. So they could do a bunch of things, but most important, I think the pinnacle of all, technology development, they could center a div. So I'm just kidding. I love most of these technologies. What I mean is, the original full stack engineers were people who were trained in systems thinking sufficiently for them to become very productive, no matter at what layer of abstraction they were operating in. But the moment this became the 10x, label also came into the picture. The moment this became popular, training shops opened up, and obviously, this too became a sacrificial lamb for the training thing. So yeah, one of the major issues that happened, and I'm saying this largely from the larger industry perspective, is that training started being overemphasized instead of education. Hamming talks about, Richard Hamming, those of you familiar with the ECC, the error correction side of things, and a whole bunch of other mathematics. One of the greats of our field, he spoke about education is what, when, and why to do things. Training is how to do it. Either one without the other is not of much use. So academics will fall in the pure education bucket. Technicians will fall in the pure training bucket. I feel engineers sort of try to capture, as much, try to move around in both of these worlds to a fair degree. And this is where, I really liked Dominic's talk about formalism yesterday, where, it's so important that when we are working on a day-to-day basis in our jobs, we, as much as possible, we try to think about formal behavior, formal systems thinking. Without that, it becomes very tricky to model and predict. Anybody can put up a bunch of bricks together, but to create a bridge, you need to think what are the design parameters of that bridge, and you cannot do that without systems thinking. So with that, let's take a look at some of the recent developments and the near future. 4 driving factors that I want to talk about. One is that abstractions keep getting better. Just like I said, not everything in the last 20 years was bad. It was actually because so many people were using it and such strong focus on accessibility that the abstractions actually became better. And that will continue to increase. By getting better, I mean lesser foot guns, just because there are so many people and thus so much cost associated with those foot guns. Another driving factor is programming is commoditized. There are sweatshops that can program for you, right? They wouldn't necessarily be able to engineer for you, but they can certainly program for you, right? The third one, which I'm sure I'll get a few eye rolls about, is AI. This is one of the things that is actually going to commoditize programming, for the simple reason that it's one thing to express a computer how to behave, versus it's completely another to model it in your head how it should be behaving. Okay, and this piece where you're just articulating, in some language you're articulating to a computer what to do. This piece I feel has extremely little value left in the industry, and that value will continue to decrease. The value about reasoning, for example, how do I create safer systems? How do I extract the maximum out of my system? These are things that will continue to become more and more important, particularly with things like cloud, etc., because there's a lot of disillusionment that will also happen about the cost that actually is incurred there. Before that, another very important part about AI is that whenever consumer behavior has changed, new abstractions emerge, new paradigms emerge. And that's something which we saw in the smartphone scenario. The same thing will happen here. I cannot predict what those things are, but what is guaranteed is there will be a demand for new kind of paradigms, and which is where the systems engineering industry need to rise up to sort of present good answers there. Hardware is becoming interesting again. Bottlenecks have moved largely to the memory right now. That presents its own different ways of thinking about how we should build systems. Tiger Beetle is actually a good example of that. I also feel that NPUs will start showing up, those neural processing units and stuff like that will actually start showing up in pretty much every consumer SoC from here on. They will become really mainstream, and those will present their own programming models, their own abstractions. And there's so much, like I salivate at the prospect of just so much new stuff that is going to get built there. For those of you who follow the hardware industry, CXL is something that you might have actually heard about, which in particular CXL.cache, CXL.mem, which allows you to write in a cache coherent way directly into a CPU cache. I think those are fascinating. Those will also create fascinating behaviors and abstractions that we can really use effectively. 3 fronts of increased systems engineering. First one is a betterment of abstractions, which will show up in much better programming languages. Zig, is obviously a very obvious example there. Doing the same thing, but giving us much better nouns and verbs to reason about the behavior of the system. Rebuilding of existing products. Bun is a good example, where simply because you have much better abstractions allows you to revisit a lot of those products that are actually already out there, and a lot of money is to be made by rebuilding some of those products because you can create them much safer, much faster, just a lot better. The third one is that new abstractions that reflect a completely changed reality, and this is one area where it's very difficult to say, but AI is going to play a pretty important role there. There are a whole bunch of other effects also, leaner orgs and stuff like that. But yeah, those are the areas where I feel we'll see a lot more increased systems engineering, which is why I'm quite bullish about more systems thinking pervading in the industry, because the time of the cheap stuff is gone. So yeah, that was it. Thank you.